So I really enjoy coming to New Jersey. I was just telling Debashish because I spent a total of 1 year in New Jersey at Bell Labs, and that's where I learned all the communications. And Bell Labs folks just from Ehsan what full duplex is about. We're trying to actually communicate in the same frequency band at the same time, sending and receiving simultaneously. So pretty much all networks today use some form of half duplex, either in frequency or time. And recently there has been a lot of news. Many groups have reported different designs to and showed success at small to medium range full duplex. And like any success which has 100 fathers, full duplex already has 10. So different groups are now coming out of the woodwork saying, I did it first and I did it first. So I won't get into that. I can't settle that. Actually, all of them did not do it first. Radars have been full duplex for decades. And many of the ideas which are being implemented are actually kind of rehashed versions of what's already in the different literatures. Okay. But there is something else which is happening now, and something interesting which is happening, because most of the communication, wireless comm, is moving to short range communication. So, you know, from macro cell to micro cells, femtocells, Wi-Fi, and those are going to dominate it. And that's exactly where full duplex is actually useful. So it is kind of coming back at the right timing to ourselves. And what I'm going to tell you is only a personal storyline, what happened at Rice. So I'm not going to try to map the whole field. So around 2009, when we first started discussing this in the lab and then got some initial results, we were super excited. But quickly that led to questions of why. Why does our system behave the way it behaves? And I'll talk about trying to answer why explaining actual numbers. And then I will talk a little bit about where we're going next. And I stole this idea from Mung's. Mung has 3 nights and done. I will do 5 minutes and done. You know, the mimicry is the best form of praise, so great idea. And for the first 2 5MD sessions, I'm just going to talk about why it is difficult, and then what are the main ideas, techniques used, and then go on to explaining some of the recent results from our work. Okay. Why is it difficult? It's very simple to understand that. Just imagine for this conversation you have a transmit antenna and a receive antenna. Let's say could be your laptop, could be base station, could be your mobile handset. And for now, instead of assuming they are same antenna serving both the purpose of transmission and reception, they are different antennas. Okay. Now when you send your own signal, your transmit antenna is close to your receive antenna. So it gets a huge signal compared to what you're trying to receive from somebody far away. Okay, so that differential is huge. It can vary, and it could be anywhere from 50 to 110 dB, depending on how far the other signal is coming from. This 110 dB range you will hit in the edges of the cellular macro cells. Okay, so actually it's not very difficult problem. The problem has always been in implementation. Conceptually, it's actually very easy because you know what you're transmitting. You should be able to cancel it out. There is no rocket science here. The whole issue has always been that the analog to digital converter is always been the bottleneck. Okay, why is that the case? So I'll simplify this is a simple cartoon. You have your own transmit antenna sending a lot of energy because, or you're receiving a lot of energy from your own transmit antenna because it's very close by, compared to the energy, let's say, black signal coming from very far away. Okay, what you see at your receive antenna is the red signal, which is sum of the 2 signals. So big signal which is your own, small signal something from far away which you really care about. When it goes to your analog to digital conversion, you get a signal which is quantized, and even if you magically could subtract out all your interference you generated yourself, what you're left with has only few bits of information about the signal you care about. Okay, so even though your analog to digital converter had huge number of bits, let's say 12 bits, you may only get 1 or 2 bits of information, which is not very useful to actually build a whole communication receiver. Okay, so even just For a 12-bit ADC, which is already at the high end of what's implemented in mobile devices, 35 dB of differential kills the whole, kills the receiver. Okay, so what you need to do is somehow suppress this interference before it hits analog to digital conversion. Okay, now one could say, well, let's just wait for the technology to scale. We could just use better ADCs. Unfortunately, ADCs, there is no Moore's law for them. They are actually governed by thermal noise, and in fact, there is no consensus on the limits of the technology. But there is, if you look at past 2 decades of ADCs, they have only improved by 1 bit per decade. That's it. That's the improvement. So the curve is extremely slow. And in fact, there are some papers which have actually tried to quantify how well ADCs, how, what kind of, what are the bounds on ADC based on actually some physics-based principles, actually Heisenberg uncertainty. Okay, so we won't get into that. We'll go to the next 5 minutes and done session. What are the ideas people are trying to actually deal with this problem? Okay, so you have all these different ideas. They all look very different. Okay, but they can all be actually classified into 3 boxes. Okay. Okay, and they are all essentially trying to engineer, change the self-interference channel. The self-interference channel is what is between your transmit antennas and your receive antenna. You're trying to change it how it looks like, how strong it is in its composition, because that's the culprit channel. Okay. So what we really have, the simplified picture here is, there is a transmit antenna sending a lot of interference. You have some signal coming from far away. You have a sum of the two. What you really care about in the design of these schemes is addressing that H sub I, that channel, the self-interference channel. So if you just look at this chain, which has the signal you're sending, goes through an up converter, gets transmitted, goes through a channel, is received on your own receive antenna. And one of the first techniques you do is try to increase the path loss, propagation loss of HI. Okay, you don't like this is too strong, let's dampen it. Okay, this is a different, opposite problem of what you typically do in a wireless, where you actually want to increase the receive energy, so you want to decrease the path loss. In this case, you want to actually increase the propagation loss seen by H sub I. Okay, so that's it. Those are the techniques which actually try to do that. They can be kind of broadly classified as passive suppression techniques. Okay. The other set of techniques heavily rely on the fact that you know what you're sending. After all, this is a signal you're forming, you're sending. Can I use this knowledge to cancel it? In fact, our brain actually does that all the time. When we talk, we can actually hear some things. This problem exists in our body, and there is a notion of echo cancellation which happens in our brain. Okay. Not when you're talking very loud. Okay, that's too much self-interference to yourself. That's why my kids can't hear me most of the time. Okay, now for this particular idea, there have been actually many published methods since 1998, quite a few. And that active cancellation idea can be divided into 2 categories: analog cancelers and digital cancelers. Okay, the analog cancelers do something straightforward, as the name. They try to actually do this cancellation in analog before it becomes a digital signal. So all this cancellation is done before it hits analog to digital converter. Okay, generally needs analog parts. You saw Ehsan's idea of using more antennas and phase shifting them, and there are other ideas which actually try to do so, but they all essentially try to do the same thing. They realize there is a path going to your antenna or before your ADC. Let's try to create a cancellation, a negative of that path somehow. Okay, so all of this using the same basic idea. And then there is the digital version, which is where you say, I'm going to anyway bring it to digital, and that's where I know what I sent. Can I use it there? And that's the other form of doing it in baseband. Of course, it is useless if the ADC is the bottleneck. So you have to do some analog cancellation. All right, so we actually built all this on Warp, which is just one slide on it. It's just a platform we started building many years ago, and then it actually spun off as a company, and the company manages the production and sales of it. We manage at RISE. I manage mostly the open source aspect of it. So we built new design flows. You saw Ehsan use Warp Lab. That's the design flow we built, and then actually we built real-time design flows, so you can actually assemble together networks out of the box. So fully functional physical layer and MAC layers. As of yesterday, Mango tells me that they have 125 plus organizations which have adopted it. And I think there is like around 140-50 papers written using Warp now. Okay. So we actually built our own version of this MIMO full duplex. We built a full 20 megahertz OFDM implementation, put antennas on the lab, built an analog canceller, put the digital canceller, threw the whole kitchen sink at the problem. And thought about antenna placement. Here is a laptop, multiple antennas placed in different places, and built a 5-node test bed which could run 5 different physical layers, several of full duplex physical layers, and then several half duplex physical layers. Whatever we could build in that, ran a month-long trial with regular office environment, just people walking around, what you would see in a Wi-Fi deployment. And that was the end result. The whole month long, there was the end result of what we found out, that a 2x1 full duplex beats out a 2x2 MIMO system for a range of SNRs, which is somewhere from 15 dB to 30 dB. Okay. The reason we care about this range of SNRs, Wi-Fi is designed to operate from 0 to 30 dB. Okay. Actually doesn't, if you give Wi-Fi more SNR, it doesn't actually exploit it. So that was kind of important because most of the full duplex demonstrations, if you look in the papers, actually operate in this regime. They're above 30 dB of SNR. In SNR, you don't see in Wi-Fi actually. So it was good for us to see for the first time that we can get into a space which is practically useful. Okay, so at this point, when I saw this, I said, I'm convinced, I'm going to work on it and more. Okay, not just a headline, not 15 seconds of fame, but actually something could be a research area of sorts. Now the question became, how do we push this threshold, which is where the full duplex becomes better than the towards left. I wanted to have a better performance in even lower SNR. Okay, in fact, possibly all the way down to 0 dB. That would be fantastic, right? Then I will have lots of flexibility, and that led to asking the question, why do we see the numbers we see? Okay, so and that's kind of difficult question. That's the difficult question of running experiments, to explain experimental numbers. Okay, often we will say, this is how it is. There's actually a lot of experimental papers essentially stop there. Now that's not acceptable in physics. If it was, then Einstein would be wrong and neutrinos would be faster than light, right? Nobody got the joke. But that was happened 2 years ago when when there was experimental results reported that neutrinos have been measured to be faster than light. Turns out there was a hardware glitch in measurement. Okay, so that's always an issue in experimental papers. If you just report the experimental results but can't explain it, that's incomplete story. So that's where we found ourselves. So we need to explain our numbers. Okay, so different papers were reporting all these numbers, some 34, 30 dB, these are numbers from our work and other people's work. First question was, why these numbers? Why 34? Why not 35, 36? Why these numbers? Okay, and then it turns out there was another thing we had observed, that if you put these analog and digital canceller in concatenation, the sum total of cancellation you get, how much you can suppress the signal, is not additive. Actually, it's barely additive. It's dominated by the first thing in the chain. So I won't explain this today. I don't have time. But actually, it's explained in the paper why this happens. But I'll explain the first question. Okay, that the reason why all these analog cancellers have a bottleneck as of today, implemented on these off-the-shelf platforms like Warp and GNU Radio, is there actually bottleneck is phase noise. Okay, and then let me explain it quickly. Okay, so this is the same the old picture I talked about. This is your transmission path. You're up converting your signal. It is going through the self-interference channel, and you create a cancellation path whose objective is to cancel the signal at your receive antenna. Okay. All right. So in fact, turns out all those 4 techniques I mentioned actually fall into one of these 2 categories. They are either a pre-mixer techniques or post-mixer technique. Mixer is nothing but which converts a baseband signal to your passband signal. Okay, it just upconverts the signal. So either they do something before, or either they do something afterwards. Okay, and in fact you can label them. The rise design is the only pre-mixer design, others are post-mixer designs. All right, so why, again, first question, why the rise design gets 34 dB only? Okay, so in this simplified picture, you could either make errors in the upconversion process, or you could make errors in the implementing how to create the interference signal, the cancellation path. Okay, so we will look at a very simple channel, which is just a channel gain with a path delay. So it's just one tap, something going from here and then reaching at the receive path after some delay, and then actually put in how an oscillator really looks like. All oscillators are imperfect. So even if you want to upconvert to a frequency omega, in Wi-Fi that is 2.4 gigahertz, in cellular that's somewhere between 1.8 to 1.9 gigahertz. You will not be able to do it accurately. You will have a random phase noise in the process. You will have a jitter, something you cannot get rid of. You can only make it smaller by better designs. So if you actually do this and you pass your cancelling signal, which looks like this, which is very straightforward to derive, what you find is that the same phase noise which is generated by that oscillator is now going through different channels. The top channel delays after you upconvert, the bottom channel delays before you upconvert. As a result, you end up with the residuals on the other side. You can't get a zero in this case. Okay, and then the residual actually has a very simple to derive approximation, which you can see visually. That means as the phase noise variance increases, as you get more and more noise in the system, the amount you can cancellation decreases. Okay, turns out that the warp radios have around 0.7 radian phase noise figure, which you can read off the data sheet, and you should not be able to do more than 36 dB. That's the maximum you can cancel in this system. Okay, and we actually took a signal generator. It had a much better phase noise figure. You can actually go all the way to some 57 dB of cancellation, huge cancellation compared to what we do. Okay, we actually then built it. This was what the analysis predicted, and then we actually built the equivalent of that system and showed that actually the numbers we observe experimentally match really well what we are predicting. More importantly, what our prior results had shown that you have 34 dB of cancellation. That's because another effect of imperfect channel estimation is also coming into the mix. Okay, so this was great. Now we are beginning to understand that what is the bottleneck in this design, and if I improve the bottleneck, my designs will get better. So they give you a design guideline for RF designers as to which part of this whole system they should focus on. Okay, so not only we could explain our results, we are actually beginning to look at other people's results in the same model. And if you look at this post radio canceller, which is all the other designs which I showed, you should be able to get actually zero residual, because there is no difference in the way it's being applied to this. Both paths are delaying the phase noise same amount. Turns out, of course, nobody can claim zero residual. All of them are finite cancellation. They are not infinite dB of cancellation. Okay, and in fact 3 out of these 4 are done on warp, so we know exactly what their radio characteristics look like. Okay, so that was a good part of having a common platform. We can actually start to look at each other's results and explain them. And then what we found out that this was a Stanford design which was reported, achieves around 45 dB. Our narrowband prediction is around 50 dB. So there is a wideband loss which we actually know how to quantify. So we are actually close to being able to explain other people's result too. Okay, so that takes care of understanding the analog canceller bottleneck. Now I'm going to talk about the antennas. After all, it's all about antennas sending something, receiving something. So remember, there was this slide I flashed by quickly where I said we have some median 85 dB of cancellation. The dirty secret of full duplex is that 85 dB is dominated not by these techniques which I mentioned. not the active cancellation. It's actually, most of its contribution comes from a better antenna design. Okay, passive suppression dominates it. So even though there's a lot of activity and papers written trying to do better active cancellation, really perhaps the bigger bang for the buck may come from just better antenna design. Okay, so we decided we're going to study this more. What's the bottleneck in our antenna design? Okay, so I'll oversimplify this discussion. This is what we are essentially happening. You have a full duplex node, you have a transmitter and a receiver, and there is a direct path. But actually there are other local reflections too. If you take your phone here, you would get a direct path here, but you may actually get ground bounces from other things. Okay, those are the local scattering the devices will see. Most of the passive design ideas actually address the direct path. Okay, so for example, this is what that 85 dB number was based on, by trying to put transmitter and receive antennas on the other side of the devices and using the device to attenuate the signal. Okay. Then we actually had, we tried different ideas. These are all exist. They're all in simple antenna ideas. You can actually buy an RF absorber, which is just an attenuator, a resistance to RF signal. Looks like foam. If you put between two antennas, it will reduce the signal by 20 dB or so, depending on how it is. Or you can use cross polarization. One antenna, transmit antenna may go vertically polarized, the receive antenna goes horizontally polarized. Works beautifully when they are close to each other, but also works nicely when they are far from each other because the reflections depolarize the signals. Or you can decide to do some directional communication. So once we had these ideas, we started to put together and think about how we will build an infrastructure node, your new AP, which will have full duplex in it, and we can actually put together all these ideas. And we wanted to see how well we can do with these. Okay. So we actually build different configuration using off-the-shelf antennas, use different combination of directionality, absorption, cross polarization, and then we are fortunate we have access to NASA's anechoic chamber. Okay, so we went to the anechoic chamber, tried all these configurations, and we found out that actually you can push this. In anechoic chamber is nice because the reflections are what get suppressed a lot. So you can understand how much can you suppress the direct path. Okay, it turns out you can suppress the direct path up to 74 dB. This is actually already the number which people reported with active cancellation into the mix. And we haven't done any active cancellation, just a proper design of antennas. However, the same antennas have a miserable performance when you put them in a room which has a little bit of reflection. Actually, this room has a lot of reflection, so this is like the worst case scenario. But you can see reflections are the ones, what this shows is that the reflections are the ones which really affect your passive cancellation. So if you could control them somehow in your deployment, you could get a huge bang for the buck. So thinking was, where can you control them? Infrastructure. Mobile nodes, you don't know what's next to you, can't control reflections. Okay, so we decided we will do this. We took our system, took it outside and started extending it further and further away. We had a 120 meter long wire. That's where the experiment stopped. That's why we have gone only to 120 meters. But we showed, the experiment revealed that actually you can get a huge amount of interference suppression if you combine the passive ideas I talked about with the active ideas I talked about, put it all together, you can almost start hitting noise floor on an infrastructure node. Okay, that means that infrastructure can be made so capable that you don't actually have to worry about self-interference. Okay. All right, so that was good news. We said, okay, we're going to make, now we essentially designed a very good piece of infrastructure, but what about mobile handsets? Okay, can't apply any of these ideas. My iPhone is getting smaller and thinner. Already real estate is a big issue on small devices. But there was a question in the morning, there are many opportunities where a node may not have traffic board directions, uplink and downlink. Okay, so we said, actually that may be the first scenario where it gets deployed. That the infrastructure is full duplex. It can handle an uplink flow and a downlink flow at the same time. But all the mobile nodes may be half duplex. This system, if it was possible to handle both these communications simultaneously, will still give you 2x gain. Just like the full duplex system, any other full duplex system between two nodes. Okay, so that was good. So that's a good idea to try. Maybe we have half duplex nodes. You don't need to change your mobile handset, only change your infrastructure. Leads to a new problem. You can see now there is an internode interference. Transmissions from this guy are interfering with this guy's reception. Okay, so in fact you can look in the information theoretic bounds how well that previous system I mentioned can perform. Actually it has a very bad news. It has a huge zone which I'll just label as a dead zone, where it is nothing better than current systems which can support one flow at a time. Okay, so 2 is the best you can do. It drops to just having one of, being able to support only one flow. Okay, so when in engineering, and this is an upper bound, there is nothing you can do. There is no hardware you can build to actually improve it or change it. So when something like this happens in engineering, you change the problem. You add something to the mix, and that's when we started asking, how do we achieve multiplexing gain of 2? How do we get 2 full flows simultaneously? We started to think about, can we mimic this, what we have done in the lab, in this scenario? And what we've done in the lab has that the receiver knows what the transmitter is doing. So can this receiver somehow know what the transmitter is doing? Okay. And unfortunately, our smart devices actually provide a clue how we might be able to do it. One possible idea. Okay, right now we actually have devices which have almost 10 radios. Your iPhone 4 already had 10 radios in it, operating in all these different bands, both cellular and Wi-Fi bands, ISM bands. So can we leverage this multi-radio capability of the devices itself, mobile devices? And then that led to this idea perhaps of how do we use ISM bands in cellular systems. Okay, right now we always actually think of them as separate pieces of bandwidth and hence separate networks. But if you actually walk around, there are many places you don't get any Wi-Fi, as prevalent as it is. Can I use that band to improve cellular communication? Okay, so I will show that actually in this case it turns out to be a great idea, where you can use the ISM band to help you cancel your cellular interference. Okay, an idea which we're now expanding to much more general cases. And in fact we came up with this scheme called bin and cancel, which you can show information theoretically is finite bit optimal for all SNR regimes. It's actually it achieves capacity up to 1 bit accuracy. All right, so I'll show just 2 plots how well this thing can do. That you have if you look at what you care about in the system is how much extra bandwidth you are using compared to the cellular bandwidth. And you see, even if I use half the cellular bandwidth, you can get a 50% boost in your dead zones. That means you actually already gotten away from dead zones, you have a 50% boost in your capacity compared to current systems. And if you use more, in this case actually let's say 5 times more bandwidth than your cellular, then you can actually get to get a multiplexing gain of 2 in all regimes. Okay, so as good as having 2 simultaneous flows which don't interfere with each other. Okay, so what's next? We are going bigger. Okay, so one of my colleagues, Lin Zhang, has taken the warp boards which only support 4 radios and have built a massive array out of it. It is a 64 antenna array. He ran out of money. He was trying to do 100 antennas. And that itself, that capability itself, going from anywhere from 1 to 64 antennas, actually is giving us lots of cool ideas of what we can do next. Okay, not just in full duplex, but just in terms of communications architecture. So we are getting bigger, and actually we have a plan to get bigger on the spectrum side too. So we are increasing our testbed capabilities in 2 directions. Spatially we have done it. Spectrally we are in the process of doing it. So we can then access huge swaths of spectrum at the same time too. Okay. And the question would be, what can you do if you're given so many new degrees of freedom to design? How would you think of network architectures differently? All right, so I'm actually going to stop. I was nearly on time, and I can take some questions and comments.
time for maybe a couple of questions. Well, first of all, we're going to, Mike, cut that part about the NASA from the video, all right? So let's take that half-minute clip.
Or you can blackmail me for the rest of my life. Yeah.
That's fine.